Architecture search is the algorithm, which is a technique to automate the process of manually designing network architectures. This is relatively a new field, which was like first introduced by a team of researchers at Google Brain a few years back. And let's see what's more to it. So the initial approaches were to use reinforcement learning, um, where a controller network is trained to come up with architectures that are then trained on the data. The objective of the controller network is to find the network that achieves the highest possible accuracy after training. The controller network takes over the role of an agent, and the accuracy score of the trained network serves as the reward. So basically, the idea is what we have been doing since like past decades was people used to manually design the network architectures for specific problems. For example, AlexNet, then we have ResNet, we had VGG, we had so many different network architectures, which were all manually designed, tested. So now this NAS came, this algorithm, what the aim is to eliminate this manual labor part and to so this program, this algorithm actually generates a model for you, generates the network architecture for you, which then you can use to train and test uh, your data set. So that was the basic idea. So and the initial approaches were to use reinforcement learning, just like they use in games. So the idea was, yeah, you have a controller, it gives you some output, you test its accuracy. If the accuracy is not very good, then it changes the policy, then it generates another architecture. If the network is better, it gives some positive rewards, so it works on that with them. So it works like that. Now, as you already have noticed, this process is very complex and thus tend to be slow and expensive because you are training model every time you're changing a policy. So this is like really expensive and really slow. So in this paper, the authors present a solution to find a cheap estimate of this accuracy uh, of this trained neural network. Now, even if this estimate is not perfect, we could use this to discard bad architectures and save time that we could use on the remaining architectures. So we use this algorithm to basically shortlist a few architectures and then we work on that. So we don't work on the whole set. We get a subset and then we work on it. So it actually cuts the time in like a lot. So that is the advantage of this paper. Now, quick disclaimer. I'm not going to talk like the whole paper in detail. I'm going to cover only the main idea behind this paper and how this could be used. So just keep that in mind. Like, okay, so going next. Yeah, you can see, let's first see the main idea behind this paper. So the authors investigated the linear maps present at initialization, and linear maps present can provide like insight on how the input space is divided by the network. If data fall into the same linear region, they are harder to break apart by the network. And linear maps are therefore an indicator of the flexibility of architecture with respect to the data. So the authors derived these linear maps from the overlap of ReLU activations. ReLU is rectified linear unit activations. Uh, it is a really common activation function used in neural architectures. So they use this ReLU activations between two data points in a mini batch, and then each ReLU layer has its own activations, which can be summarized in a binary code. Now, the lack of overlap between the activations of two data points is given by the Hamming distance between each ReLU layer for the two data points. We'll talk about this Hamming distance in next slides. So we expect that more flexible architectures have fewer shared activations. Now this figure here shows the connection between linear maps and ReLU activations. So as you can see, we have a feed forward neural network on the left hand side with two hidden layers, with each having three nodes. Now, the input space is two-dimensional, x and y. Each layer contains these three ReLU activations. So here, this A1, A2, A3, then B1, B2, B3. All these are ReLU activations. And on the right side, you can see, so this one corresponds to the separation after applying A1, A2, and A3. And now this two shows the binary code corresponding to that separation just by these three A1, A2, A3. Then the third, this number three, this shows the separation of each activation in the second layer corresponding to B1, B2, and B3. And the four again shows the resulting separation. So this was the main idea behind it. Like the authors got the intuition from this. Okay, moving over to next slide. Now, the main idea is that since these ReLU activations describe linear separations of the input data, if this separation widely varies between data points, this might indicate a mismatch between architecture and data. Now, as indicated in the previous illustration, we can also view the ReLU activations as a binary code when we combined all those three, like in the number 2 and number 4 points. Now, if we do this, we can quantify the difference between activations of two data points using the Hamming distance. Now, let's see this. If we consider a minimatch of data X um, and a network, we can define an indicator variable Ci that forms a binary code that corresponds to a linear region. Now, we use the Hamming distance between two data points, which is represented by dh, to measure how dissimilar the 2 points are. Here, our 2 points are Ci and Cj. Now, the Hamming distance is actually the minimum number of changes needed to turn one binary code into other. Or we could also say that um, it is the number of positions where the two codes differ. Now, the correspondence between the binary codes can be calculated by kh, which is the kernel matrix, and na as the number of ReLU activations in the network. And you can see the kernel metrics here. Okay. Now, so we calculated kh in the previous slide, right? Now we have plotted this kh for NAS Bench 101 and NDS darts, which is another architecture benchmark for this NAS networks. And this reveals that there are fewer off-diagonal elements for high-performing architectures. You can see the the top headings are basically represent the percentage of the accuracies. So you can see the greater than 90%, they have fewer off diagonal elements. All of the elements are majorly just diagonals. So we can use this observation to predict the final performance of untrained network. Now, yeah, these are untrained network, and this accuracy is after we train them. So yeah. So without even training, we get an idea like this could perform. This will like perform better if we train it later. So this way we can disregard it. So this is the observation we are using, and in place of the expensive training they do in neural architecture searches. Okay, and this is the main player here, the score S. So the scoring matrix is derived from the logarithm of kernel norm at initialization. So we take a log norm of kh matrix, And the authors show that this metric can be used to guide architecture search. So this is the gist of this paper. We calculate the score, and the score helps us guide the architecture search. Let's look at some of the results. Um, so these are not all the plots. They have a lot of these in the actual paper. I'm just showing three here. But in all the cases, even if you see in the paper, there is a noticeable correlation between the score of an untrained network and the final accuracy when trained. So you can see here, this is NAS bench 201, this is NDS darts, this is again NDS darts, but on ImageNet this one is Sapphire 10. So these are the scores we calculated in the previous slide, the score S. And the validation accuracies are the accuracies we get after we train the network. So we can see a positive correlation. If a score is higher, we get a higher validation accuracy. And this was true in all of the cases. Now this table actually shows the actual numerical results. So this search column is the time taken in seconds. Uh, these red colored are the NASWAT. This is another area is another work in this paper. I'm not discussing this. This is also using NASWAT. So still you can see like it takes hell less time than the others, and still its accuracy is like it's not performing state of the art, but it's still giving good results. And the actual idea is not to perform, state of the art. The actual idea behind this is you can get a subset of your search space, and then you can use those other state of the art algorithms. So that is the idea. You are basically reducing the search spaces. So in this work, the authors have shown that it is possible to navigate these spaces with the search algorithm, which is NASWAT, in a matter of seconds, relying on simple intuitive observations made on initialized neural networks. That challenges more expensive black box methods involving training. Yeah, so they are doing this without even going on training step. Just mathematically, they are doing this. So this is very interesting as the metric provides a huge speed up when performing architecture search and could be implemented as a fast filtering step. The field of fast neural architecture search is quite new, and there are some interesting developments. Now, according to the authors, the future applications of this approach to architecture search may allow us to use NAS to specialize architectures over multiple tasks and devices without the need of for long training stages. Here are some references. The first one is the link to the paper. The second one is link to the code base they are provided. That is it for the paper. Thank you all. Uh, I'll take any questions you may have now. I'll also put a feedback form in the chat, so kindly fill that as well. Yeah, so questions. Let me stop the recording first. Yeah.